Hello and welcome back. In this segment, we're going to look at actually creating a buffer, what we have to do conceptually for creating a buffer, and a little bit of math that goes along with that. And then we're going to introduce something called the Henderson equation that we're going to use to simplify a lot of equations and calculations that we do when we're working with any kind of buffer solution. We're going to use this Henderson equation an awful lot in this chapter. All right, so let's look at this first aspect. When I make a good buffer, to have a useful, viable buffer, I need to have similar concentrations of weak acid and conjugate base. Just keep in mind that I'm talking about a useful buffer, a good buffer. For a solution to be just a buffer solution, I just have to have a weak acid and its associated conjugate base, regardless of concentrations. Right? Concentrations don't determine if I have a buffer or not. Concentrations only determine if it's a usable buffer. It's a useful buffer that's going to be practical for us. Right? And for that, we have to have similar concentrations of weak acid and conjugate base. And we have a problem with that right off the bat. When I add a weak acid to water, when I add acetic acid to water, only a small fraction of that weak acid will hydrolyze, will react to form conjugate base in hydronium. So there's very little conjugate base form. I don't have similar concentrations of weak acid and conjugate base. So I need to, it's a little bit more complicated to make a buffer than just taking my weak acid, dumping it in some water, and being done. I need to add some conjugate base separately as well. So, and that's what we call the common ion effect. It is defined as the addition of ionic salt to a solution that already contains that species in solution. So basically, I need to add more of that conjugate base. However, that conjugate base is an anion. Right? I don't have a jar of anions on the shelf. I have a jar of neutral ionic salts. So that means when I pick my salt to add, I have to have two other considerations I need to think about. The cation of that salt cannot affect pH, so I want to pick something from group 1 or group 2 cations, the ones that don't affect pH, and it also needs to be readily soluble. So all of that salt gets into solution, and that just makes life easier. I don't have to worry about percent ionization of my salt, and it just makes life so much easier if you just pick a salt solution that doesn't affect pH and is readily soluble. And the obvious choice is that is use a sodium salt. Sodium doesn't affect pH, and all sodium salts are soluble. So the vast majority of common ion salts that you use, you can see are either potassium or sodium for those two reasons. They're soluble and they don't affect pH. So let's look at our example. If I take some acetic acid, put it in water, I'm going to make some acetate and hydronium. So what's the common ion here? The common ion that would be added would be acetate. So I'm adding a base. The acetate ion is a base, and this is going to change my pH a little bit. It's going to increase my pH. So it'll still probably be acidic. My pH will still probably be less than 7, but it's going to increase my pH. So let's look at an example of exactly what I mean by that. So let's calculate the pH of a 1 liter 0.25 molar acetic acid solution. And we're going to do two calculations. We're going to calculate just that solution, and then we're going to calculate it again after I add 0.10 moles of sodium acetate. And so we're going to have two pHs, and we're going to see how they go. So according to the previous slide that we said, after I add that sodium acetate, my pH should increase. Let's do the first part. So we write our reaction. Right? And what kind of reaction is this? This is just a hydrolysis reaction. This is just chapter 16 calculation here. There's nothing new with this part 1 that we're doing. I'm just calculating the pH of the 0.25 molar acetic acid solution. We look up the Ka for acetic acid, 1.8 times 10 to the minus 5. So I set up my ice table. This is no different from chapter 16. Right? We have our Ka expression. Ka is equal to x squared divided by 0.25 minus x. We stop and we ask ourselves, is our assumption valid? It is. 100 times our Ka value is 1.8 times 10 to the minus 3. That certainly is smaller than 0.25. So the minus x goes away in the denominator. Simplify our calculation so I don't have to do the quadratic. From here we just solve out. My x value, which is my hydronium concentration, works out to be 2.121 times 10 to the minus 3 moles per liter. Take the negative log of that. My pH is 2.67. Right. So that's all we need to do for pH before. And again, this is straight chapter 16, nothing new here. Right. Now let's do the pH after, and let's consider this added sodium acetate solution. Okay. So basically we're going to do just about the exact same calculation again, just slightly different because now we have the sodium acetate that we added. I'm going to leave my reaction exactly the same. I could flip it around if I wanted to, but I'd have to convert my K value, and that's extra work. So don't bother doing that. Just leave the reaction exactly the same. So I can use my exact same Ka value, 1.8 times 10 to the minus 5. This time when I set up my ice table, everything's the same except for the conjugate base, because now my initial value for conjugate base isn't 0, it's 0.10. And that just changes the initial value and the equilibrium value is now 0.10 plus x. That's all that's different and that's all that's new. Otherwise, this is still a hydrolysis problem. So we're going to solve it and approach it the exact same way. Set up my K value. Ka is now x times 0.10 plus x divided by 0.25 minus x. And we still have our assumption rule. And our assumption is still valid. It's just now that I have initial values for both acid and conjugate base, I have to apply my assumption 100 times my K value to both the acid and the conjugate base, and it has to work for both. It's an all or nothing thing. Right? If the assumption works for one and not the other, you need to go and do the quadratic. If it works for both the plus x in the numerator and the minus x in the denominator both go away. So that really simplifies down my calculation. It's even easy now. I don't even have a squared term to deal with. And now my hydronium concentration is 4.5 times 10 to the minus 5 moles per liter. That gives me a pH of 4.35. And indeed, like we saw, adding the acetate, adding a base, is going to increase my pH. The pH after my addition is higher than the pH before. But now I have similar concentrations between my acid and conjugate base. So now this is a good buffer. When we did the pH before, that was still a buffer system. And it just wasn't a very good buffer. And I've said this a bunch of times, and that's a really, really important distinction to make. All right, so now let's look at this Henderson-Hasselbalch equation. This is an equation that we're going to use to simplify our calculations for anytime we do a buffer calculation. So as soon as you recognize that you have a buffer solution, either the question says buffer, or you recognize that at the end of an ice table you have a weak acid and conjugate base, you can use the Henderson equation to solve for your pH. And we're just going to take a minute and derive the Henderson, and it's a real simple derivation. We're going to start with our Ka expression, and we're just going to rearrange it and solve for hydronium. So here's our Ka, and when I rearrange and solve for hydronium, it looks like this. And I pulled the Ka out to the side for a very simple reason, because K is our constant. That's not going to change until I change and I use a different acid base system. Right? So what I see here is this acid to conjugate base is a ratio that defines our hydronium concentration, which essentially is our pH. So the amount of acid to conjugate base is going to determine what our pH is. Right? And we just apply a factor of our K value, whatever that happens to be, to that ratio. So from this, I'm going to simplify this equation down a little bit by taking the negative log of both sides. So that gives me the negative log of hydronium equals the negative log of my Ka value minus the negative log of my ratio. I don't want to break my ratio up. I want to leave that intact. So I'm going to keep that in parentheses and take the negative log of that. Well, we know the negative log of hydronium is pH. The negative log of Ka is pKa. And then I have the negative log of my acid over base concentration. And I'm going to make one final small algebraic change. I'm going to flip my ratio around. Instead of acid over base, I'm going to call it base over acid. And that just changes the negative sign to a plus. So my final version of the Henderson equation is pH equals pKa plus the log of my base divided by my acid concentration. So anytime you see the word buffer, you want to think about this equation, and 9 times out of 10, 95% of the time, you're going to use this equation in some way to solve the question that I'm asking you. So let's take a minute and look at this equation and what this means kind of qualitatively first. I like to look at equations and use them more than just number crunching tools and devices. I like to use them qualitatively. What do the components mean? We already know what pH and pKa mean. We've talked about that in chapter 16, the relationship between pH and pKa and stuff. So let's focus on this conjugate base over acid ratio. So I've got three different scenarios with this ratio. If my base equals my acid concentration, that gives me a ratio value of 1. So I have the log of 1. What's the value of log of 1? If you don't know, hit pause and pop that into your calculator. Yeah, the log of 1 is 0. And therefore, pH equals pKa. It gets really simple. When I have the exact same amount of acid and base, pH equals pKa. Done. I have no more calculations to do. If my base concentration is larger than my acid concentration, then that ratio works out to be some positive value. Right? The ratio is some value greater than 1, and the log of that is some positive number. That means that I have pH is equal to pK plus some number. pH is going to be greater than my pKa value. And if I flip it, if my acid concentration is bigger, then that ratio is going to be a value less than 1. The log of a decimal value is a negative number. So my Henderson equation will be pH equals pK minus some number. Therefore, my pH will be less than pKa. This is important to do. You can use this to make some predictions as to where your pH should be. If you just look at your base and acid concentrations, you can make a guesstimate as to generally where your pH should be. One, it's going to be close to your pKa, because that's what we need to have for a good buffer system. But we can determine is it going to be greater than the pKa or less than the pKa. Because the number one mistake people make when they use this is they put the ratio in backwards. They put in the acid over base ratio. And as soon as you do that, you will never match your prediction. That's a real quick way to determine if the math that you did and the number crunching that you did is right, or if you push buttons on your calculator incorrectly. It's a really easy, quick check to make. So let's look at an example. Let's calculate the pH of a buffer solution of 15 grams of sodium bicarbonate and 18 grams of sodium carbonate. And the pK of bicarbonate, which is going to be our weak acid, is 10.32. So based on this pKa value, is bicarbonate a good acid? No, this is this is a high pKa value. Bicarbonate is not a very good acid at all. We have our reaction. We write it just as a hydrolysis reaction always. Our bicarbonate plus water goes to carbonate and hydronium. And we do this because we've got a K value. We're dealing with Ka, so that has to be an acid hydrolysis reaction. So let's look at figuring out our bicarbonate concentration. So I have 15 grams of sodium bicarbonate. I have to consider the sodium in order to find my number of moles. That gives me 1.79 moles of bicarbonate in 1 liter, so that's 0.179 moles per liter of my acid. We'll do the exact same thing for the sodium carbonate. Divide the 18 grams by the formula weight. You can figure that out if you want and do that math. That's just mass divided by molar mass. Gives me 1.7 moles of carbonate, which is 1.70 moles per liter of my base. So what do we predict our pH to be? What do I have more of? I have more acid. And its conjugate base over acid is our Henderson. Are similar, therefore the pH and pK will be similar too, right? But we're going to be a little bit less. But these values are really, really similar to each other. So let's get into our Henderson equation. Plug in our pKa value and our concentrations. Our base 0.170 in the numerator and our acid 0.179 in the denominator. That gives me a pH of 10.32. Very, very similar, but slightly less because our concentrations are very, very similar, but the acid is slightly bigger than our base concentration.